Welcome to this video on graphing polynomial functions. Before we start actually learning how to graph polynomial functions, I want to take a minute to talk about the scaling of the axis on a graph by showing you an example. Later in this video, we're going to see and be asked to graph this polynomial function. We're not ready to actually do that yet. I wanted to share some thoughts with you first. Now, the ultimate goal here by the end of this video is to be able to graph such polynomials without a calculator. But to just share a thought with you, I graphed this thing using computer software, and I got this picture. And it left me wondering a bit because there seemed to be a gap here between two pieces of a graph, and I wondered if they connected or not. By the way, the reason why there is such a gap, and they do connect, by the way, somewhere down around negative 100 and something, but I can't see that far down because of the way I put the settings in my graphing calculator. Notice the y-axis scaling is such that I can't see down below negative 100. So I don't actually see the meaning of these two pieces of the graph. But that may be okay in some contexts because in exchange for not being able to see that, I can see a lot of the detail here, especially between x equals 0 and 2, that might be of interest to me when graphing this thing. Then, to take a look further down the graph, I graphed the same function using the same software, but this time I altered the scaling of the x-axis so that I could see down below negative 100. And the good news here is that when I rescaled this, I was able to see this local minimum right here and get a broader view of what this graph would look like. But by rescaling the axis enough to see that low, I paid a price. I could no longer see all that rich detail between 0 and 2 that I could in the previous scaling. So if you were a scientist graphing this function, you would maybe want to look in different scalings of the axis to get an overall picture of how this function behaved, both on the close-up view and the far-out view. But in this video, we're going to be graphing these things without a calculator. So when we do this, we'll end up drawing our graphs something like this. Now remember, I haven't gotten to the point of the video yet where I'm showing you how to do this. I'm simply saying that we're going to draw the graphs in such a way that we can see all the key features and all the detail. Now, when we do this, there's a price that we pay. We get a disproportionate scaling, most notably on the y-axis. For example, in this picture, the positive y-axis and the negative y-axis are scaled differently. And this really isn't proper graphing technique if your goal is to get a two-scale graph. But our goal here in the non-calculator rendition of these problems, where we're just sketching them by hand, is not to get an accurate scaling. Rather, it's just to get a general sense of where the function is going as x goes from negative infinity to positive infinity. So we leave all the scaling off the y-axis because we're not interested in that kind of accuracy. And as far as the scaling of the x-axis goes, we don't typically put tick marks there either. But what we'll see as this video goes on is that we're very interested in the x-intercepts of these functions. So we'll label those. And by the way, I don't expect you to know where I got those at this point, but those will turn out later in the video to be the x-intercepts here. My point being, we label the x-intercepts and nothing else, because that gives us a general sense of where this graph crosses the axis, where it's above and where it's below, and the general direction and behavior near the intercepts and at the ends of the graph. So again, we're not graphing things to scale. We're mostly interested in the intercepts and the directionality of the graph. And if we can determine that, which I will teach you in this video, then that's all we care about when we're not using a calculator to get the result. Of course, this raises an interesting question. Why on earth would we bother to graph polynomials without a calculator? Is it because we've been doing this in mathematics for 400 years and it's a tradition to learn it that way? There's some truth to that. But I think it's bigger than that. I think when we train ourselves to graph things, and in particular in this video, polynomials, without a calculator, then we get a deeper understanding of what drives these functions and why they behave the way they do, why they cross the x-axis where they do, and so on. So by training ourselves to do all of this without a calculator, we get a more general picture of how the functions behave and a better understanding. Otherwise, we're just typing stuff into a screen and getting a result. And there's not much learning there, is there? So the first thing to consider is, do you have the prerequisite knowledge for this video? Well, that depends on the course you're in and what you're going to be expected to do. For example, we're going to be graphing these three polynomial functions in this video. And when a polynomial is written this way, as separate terms from highest degree to lowest, as you can see here, we say that that polynomial is in standard form. Now, for every standard form polynomial, there is a rewriting of that polynomial in what's called factored form. And it's the same polynomial with just a different expression on how it's written. Now, here's where the issue of prerequisite knowledge comes in. If you are in a course where they will be giving you the polynomials already factored, then there isn't a lot of knowledge ahead of time that you need for this video. On the other hand, if you are in a mathematics class in which you will be given the polynomial in standard form, then you're going to need to write it in factored form yourself if you're not going to be given that format. I've produced a video on how to convert from standard form to factored form. It's not covered within this video, but it's something that you can view separately, and maybe you will need to view before that. Again, it all depends on your current situation. If you're given the polynomials in factored form, you can get right into the sketching of the graph without a lot of work. But if you are, as the student, are expected to factor them yourself, then you'll want to watch this roughly 30-minute video that I've made reference to here beforehand, so that you can understand where these factorizations come from. All right, so let's take a look at our first example. Suppose we wanted to graph this polynomial. Well, one of the things that we care most about when graphing polynomials is the x-intercepts. And how do we find an x-intercept? Well, as you probably know from other classes, we find x-intercepts by setting y equal to 0. Now, if you look at the structure of this equation, what is it saying equals 0? If you look at the right side, you see the sum of 4 terms equals 0. Well, what does that mean? If 4 numbers add up to 0, what do we know about those numbers? And it turns out not really a lot. So we can't tell a lot about this equation from its current form. This is why we prefer the factored equation. Now, I didn't show the work here, and it would take the typical student about 5 minutes just to factor that, maybe 3 to 4 minutes, depending on your skill level. And again, if factorization of polynomials is not something that you are competent at, but yet you are required to do it for your course, you're going to want to go back and watch that other video. But I'll proceed in this problem assuming that you either understand how to factor polynomials as shown here, or that you're being given already factored polynomials when doing these problems, which is often the case. Either way, let's proceed. You see, this equation is fundamentally different than the last one. Previous equation showed 4 numbers adding up to 0. This equation shows 4 numbers multiplying together and the result being 0. And that we know a lot about, because if the number 2, you'll see it on the left side of the black expression there, if the number 2 times this number times that number times that number equals 0, then must it not be true that one of those factors is 0? And that goes to show the superiority of the factored form when trying to find the X-intercepts or the solutions to the polynomial equals 0. Okay, so let's take a look at the actual graph here. The first thing I know, one of the things I know, is that this graph is going to have an X-intercept at -1. I know that from this factor. You can see that if I plugged in -1 for all the x's, and then multiplied these 4 numbers together, of course I would get a result of 0, thus showing that there's an X-intercept there. I also know that this polynomial graph is going to have an X-intercept at 1/2. I can tell that from this factor. Notice if you plugged in 1/2 for all the x's and multiplied all 4 numbers together, including the 2 in front, you of course would get 0 because one of your factors is 0. And likewise, 3 is going to be an X-intercept as well. I can tell that from this factor for the same reason. So what I have now is not the entire graph of this function, but at least I have the X-intercepts, and that's a good start. Now the next thing that I would like to know in order to fully graph this function is whether the graph is above or below the x-axis in this region. Then I'd like to know if it's above or below here. Then if I could find out whether it's above or below here, and likewise here, I would have a pretty good sketch of the graph. How am I going to go about that? What I'm going to do is I'm going to plug in a random number to the left of -1, a random number in this region. Really, you could pick anything. I'm going to plug that into the original function. If the result is a positive number, I don't know yet whether it will be, but if the result is positive, then I'll know the graph is above the x-axis because I have positive y values there. On the other hand, if I get a negative answer, then I'll know that the graph is below the x-axis. And I'll do the same thing here. I'll pick a number in this region, plug it in. If I get a positive, the graph is above. If I get a negative, the graph is below. Same here, pick a random number. Same here, pick a random number. Let's start with this region. If I told you to pick any number to the left of -1, would you have picked -12? Maybe, maybe not. If you pick something else here, it doesn't really matter. Follow this logic. I want to know if this quantity is positive or negative, so I'll know whether the graph is above or below the x-axis. But wait a minute. Don't I really, for all intents and purposes, need a calculator to know whether this quantity is negative? Or maybe a better question is, would you need a calculator to know whether this whole thing worked out to a positive or a negative? I would contend that you don't need one, especially because it's in factored form. Watch this logic. 2 is a positive number. The thing in the first parentheses is a negative number. It's actually negative 12.5, but I don't care. I only care that it's negative. The next set of parentheses has a negative result. The number itself I'm not interested in. And the last parentheses has a negative result as well. Now, could I actually multiply these four numbers together? Sure, but it might not provide me with a lot of meaningful information. After all, my goal here is simply to determine whether the result of this multiplication would be a positive number or a negative number. And I can deduce that just from the plus and minus signs you see there. Looking at the bottom of your screen, I think you'd agree that if I multiply a positive times a negative, times a negative, times a negative, that I do get a negative result. Negative what number do I get? I don't know, and I don't particularly care. The mere fact that the result is negative tells me that my graph has to be below the x-axis there. What's the logic here? If x is negative 12, y is some negative number. Therefore, the graph is below the axis at negative 12, but therefore it must be below the axis on the entire interval up to negative 1 because there are no other x-intercepts or no other places that it could cross. And that's the logic that guides us through these problems. Now, let's pick any number in here. If I said to you, pick any number in that region, would you have picked 0? Maybe, maybe not. You don't have to, but any number in that region will do. Now, I want to know if the result of this is positive or negative, so that I'll know if the graph is above or below the x-axis. You don't actually need to work it out, although this one wouldn't be too difficult. The reason I don't need to work it out is because I'm in factored form, and the first number is positive. I'm referring to the 2. The next thing, 0 minus a half, that's a negative number. 0 plus 1 is a positive number, and 0 minus 3 is a negative number. And regardless of the numbers themselves, a positive times a negative times a positive times a negative will always work out to be a positive. So what does this show? It shows when x is 0, y is some positive number. But therefore, I can conclude that the graph is above the axis everywhere in that interval from negative 1 to a half, because if it's above when x is 0, it must be above everywhere in that interval. Why? Because it can't cross over the axis anywhere else. I've already found all the x-intercepts, and I know there aren't any more. And the logic continues again. Pick a random number in here. I picked 2.8 just to prove a point that it doesn't really matter. If I pick 2.8, which is in that interval, I've got my 2, which is positive. My first set of parentheses, that would be positive. My next factor, also positive. And my next factor would be negative. And as you should know, a positive times a positive times a positive times a negative is a negative. And if y is negative when x is 2.8, y must be negative on that entire interval, and therefore the graph is below the axis there. And lastly, we'll pick any number over here. I picked 100 just to make it seem obvious that it doesn't matter. When x is 100, I've got a positive times a positive times a positive times a positive, which is a positive, thus proving that the graph is above the axis on the interval from 3 to infinity. Now, I have a general sense of what this graph is going to look like because I know when it's below the x-axis and when it's above. For example, on this first interval, it's below the x-axis. Therefore, it must look something like this. Now, is that actually scaled properly? I doubt it, because I'm not trying to scale these things properly. If I wanted a perfectly scaled graph, I would use a calculator. The whole point of this video is to learn how to do this without a calculator, to increase our brain power and to understand how functions behave. So I'm not going to worry about the particular scaling or location. I'm simply going to draw something below the axis there. Likewise, on the next interval, the graph would have to be above, which means it's going to look something like this. Is it going to go higher than that to reach that local maximum? Don't know, don't care. Next interval is going to be below, so it's going to look like this. And the next interval is going to be above the x-axis, so the graph will look something like this. Now, because this is a video production and I have a sort of a neatness thing where I care to some degree about quality, I'm going to replace this hand-drawn sketch with a computer-drawn sketch. But you as a student wouldn't be expected to do that. Again, if we wanted computer-drawn sketches, we'd use a graphing calculator, contrary to the whole point of this learning exercise. The last thing that's missing is the y-axis, and I like to put the y-axis in last. Because I've found that if I put the y-axis in early, it becomes a visual distraction. Now, you can pretty much, because we're drawing a sketch, you can pretty much put the y-axis anywhere you want. You don't have to worry too much about the proper scaling. But remember, the y-axis does occur at x equals 0. Therefore, you have to draw the y-axis somewhere between -1 and +½ It doesn't really matter where, of course, because we're not worried about the proper scaling of the drawing. But for example, if you were to put the y-axis between 1/2 and 3, that wouldn't make any sense, would it? Okay, there is our first example. Let's take a look at another one. Suppose we were asked to graph this function. Well, I've got 5 terms in this function, and I don't have any factors. And I can't really tell a lot about the x-intercepts, which is our primary focus, if I don't have it in factored form. Now, one of two things is going to be true for you as a student, depending on who your professor is, and even if it's me, which of my classes you're in. In some classes, I would have you, or your professor would have you, go through all the trouble of taking this polynomial and factoring it. That's a whole separate concept not discussed in this video, but again, you can watch the video I referenced earlier to see all the details of that. It's quite extensive. Or maybe you're in a class where you're given the polynomial in factored form already and don't have to do that. That I can't address now, but nonetheless, there is the factorization. So I'm going to start with an x-axis and try to find my x-intercepts. The first x-intercept I notice is +2. Why? Because if I plugged in 2 for all the x's, this factor in particular would become 0 squared, which would then multiply by the other factor and make 0. So that's going to be my first 0 of this function. The value which I plug in to get 0 is 2. Now, this function, as it turns out, has no other x-intercepts because this factor here can't be 0. There's no number for x that would make that 0, unless you went into imaginary numbers, which for graphing purposes aren't relevant because we're graphing real coordinates. So for our purposes, this equation has no solution, and therefore there's no real x-intercepts that are generated by that second factor. So I'm in a situation now where I have only one x-intercept. So here's my plan. I'm going to plug in a number on either side of this x-intercept to find out where the graph is above the x-axis and where it's below. Let's start by picking some random number on this side. Anything less than 2 will do here. I chose -3 for no particular reason. Now, I really don't want to work this whole thing out. I just need to know if each factor is positive or negative. The first factor is positive. Wait, doesn't that work out to -5? Yes, but it's being squared. And -5 squared is positive 25. So that first factor is positive, including the square that comes with it. The second factor is also positive, and a positive times a positive is a positive. So what does this tell me? It tells me that when y is -3, when x is -3, the y value is some positive number. That tells me that the graph is above the x-axis on the interval from -infinity through 2. Now I'll pick a number from the other side. Random number chosen is 7, for no particular reason, just that it was to the right of 2 for that reason, I suppose. If this thing works out to a positive, I'll know my graph is above the x-axis, but if it works out to a negative, I'll know that it's below the x-axis. But the first factor is positive, as is the second. And a positive times a positive is a positive. And so therefore I've concluded that from 2 through infinity, my graph is above the x-axis as well. So if this graph is above on everything to the left of 2, then it must look something like this. And if it's above everything to the right of 2, then it must look something like this. And I'm essentially done with this graph now, other than putting in the y-axis. Now, if you were a student in a math class and you were handwriting out your answers, this answer would be fine. But again, because I'm doing a video production here and I want you to see what polynomials look like when graphed using technology, I'm going to put in a more accurate scaling here. And you might notice something weird to the left of 2. It has kind of an extra little wiggle or change in curvature there. Your calculus teacher will describe for you if you take calculus at some point. I'm assuming if you're watching this video, you probably aren't in calculus yet. But your calculus teacher will talk about inflection points and changes in curvature. And as a student in a class pre-calculus or lower, you're not expected to know that there's this funky change in curvature there. So really just any parabola-looking drawing whose vertex is at 2 would be fine. Again, that slight change in curvature isn't something that most students at your level would be expected to know, but that is what happens there, by the way. More on that in calculus if you go that direction. All I have to do now is put in the y-axis, and you can put the y-axis essentially anywhere you want to the left of 2. We couldn't put the y-axis to the right of 2, could we? So I put it in its actual location, but again, I happen to know from calculus that the y-axis happens to the left side of that funny change in curvature, and that's not something you would necessarily know or need to know at this point. So that completes our second example. Let's take a look at one more final example. Suppose we wanted to graph this thing. Well, again, we can't tell much about the x-intercepts until we have it in factored form. And again, that's a very intensive process, but it's not part of this video. Once you have the polynomial factored, we can tell what its x-intercepts are, and then get a good sense of the graph. The first thing of note is that we're going to have an x-intercept of 1. Because if all the x's in this problem were 1, this factor would become 0 cubed, which is 0, which would then multiply everything else out to 0. I hope you can see the benefit of factored form here. But we also have 2 more x-intercepts, and they're these numbers. Where on earth did that come from? Well, they came from this irreducible quadratic here. What I did was I set that factor equal to 0, used the quadratic formula, did a lot of messy algebra, not shown here, But using the quadratic formula, I found out that the two solutions to that equation, in other words, the two x-intercepts that are generated by that factor, are -2 plus or minus radical 3. If the quadratic formula is something that you haven't seen in a long time, go to my YouTube channel, Residual Math. There's a video on it. Now I have my 3 intercepts. But notice these 3 intercepts divide the number line, or my x-axis, up into 4 intervals. And what I'm going to have to do now is plug numbers from each of those 4 intervals to determine whether the graph is above or below the x-axis. I'm going to start over here. Now, some students would tell me that it's difficult for them to pick a number over there because they don't know what -2 minus radical 3 is as a decimal. Well, without a calculator, you can estimate what -2 minus radical 3 is. Follow this logic. Radical 3 has to be less than radical 4. If radical 4 is 2, then radical 3 must be 1 point something. And -2 minus 1 point something has got to be -3 point something. So that intercept is about -3 point something. I don't know the something, and neither would you have to. But if it's -3 point something, I could definitely pick -5 to be sure that I was significantly to the left of that first red dot, that first x-intercept. Now, I want to see if this thing works out to a positive or a negative. Well, first of all, the equation, once I factored it, started with a -1 lead coefficient there, or lead factor, I should really call it. So that's just the negative in front of the whole thing. How about the -5 minus 1 cubed? That's going to be negative as well. But remember, this relies on cubing being an odd power. Follow me on this logic. -5 minus 1 is -6. -6 cubed, because it's an odd power, is a negative number. What number is it? Don't particularly care. Now, for the last factor, I had to actually manually work it out. I think it worked out to 6 or something, but the point is it works out to a positive number. You don't need a calculator for that. And now that I know each factor's sign, and knowing that a negative times a negative times a positive is a positive, tells me that the graph is going to be above the axis on that first interval, from -infinity through that first intercept. Let's go to the next interval. What number is between -2 minus radical 3 and -2 plus radical 3? Well, one such number would be -2. If you don't see the logic there, you can estimate both of these. The first one we talked about is -3 point something. The other one, the -2 plus radical 3, given that radical 3 is 1 point something, that would have to be -0 point something. So -2 would clearly be in between there somewhere. Okay, so first I have a negative as my lead factor there. Then the next factor is negative. And I worked out the next factor just sort of on scratch paper, and I got a negative number. The point being, a negative times a negative times a negative is a negative. And therefore, my graph's going to be below the axis on that interval. The same logic will determine the next two intervals as to whether the graph is above or below. So let me speed it up a bit here. Pick any number in there. I picked 0. How do I know 0 is in there? Because that intercept, -2 plus radical 3, is approximately -2 plus 1 point something, which is negative, and therefore 0 is between the intercepts. This led me to a negative in front times a negative factor cubed, which is negative, times a positive. And that all multiplies out to be a positive, as we know, and therefore the graph is above. Finally, picking any number out here, I just picked 4 at random, and doing the same thing will give me a negative times a positive, which as we know is a negative, and hence the graph is below the axis there. You see, by picking random numbers in between the x-intercepts, I've gained some valuable information about where the graph is in relation to the x-axis, and that basically tells me what the graph looks like. So, since the graph is above on this interval, it must look something like that. I just drew any old thing going up. Since the graph is below here, it must look like that. Above here tells me the graph looks like that, and likewise here tells me the graph is going downward. Just to replace this with something that's more accurate to show you what polynomials tend to look like when graphed accurately, this is a little bit more of an accurate representation. The last thing I have to do, and I always save this for last, is put in the y-axis. Again, you can put your y-axis in at the very beginning of a graph, which is normally what students do. But I've always found the y-axis to be a visual distraction and unnecessary till the very end. But where do I put the y-axis? Well, I don't need perfect scaling, but I do need to put it between the correct two intercepts. I'm going to put it between 1 and -2 plus radical 3. As we discussed earlier, -2 plus radical 3, even without a calculator, I know has to be -0 point something. And therefore the y-axis would have to be between those intercepts. And there's my graph. And that completes our third example. All right, so we're done with our 3 examples. And for all intents and purposes, you now know how to graph a polynomial function. And again, because we're not using a calculator and we're developing those skills in our brain, you won't have perfectly scaled graphs. But this video isn't over yet, because there's some details that are worth sharing with you about what kinds of nuance you can add to the graphs without the use of technology or any kind of other graphing calculator. So in that end, let's take a look at the behavior near the intercepts. Up until now, we've simply said that the graph will intersect the x-axis at these points, and it'll be above or below on the intervals in between. But how it crosses, or if it even crosses, the x-intercept is worth a little bit further study. So follow me on this thought process. Each x-intercept comes from a real root of the polynomial function. And each of these real roots has what's called a multiplicity. If you're not familiar with that term, it essentially means the exponent of the factor from which that root was derived. More on that in a minute. And this multiplicity, or the exponent from the factor, will determine how the graph behaves near that corresponding intercept. Now this is very general, so let me give you a specific example. Let's take a look at example 1 that we saw earlier. And specifically, let's look at the factor of x minus 3. Notice the factor x minus 3 doesn't have an exponent, nor do the other ones. And since it doesn't have an exponent, we can consider that exponent, or multiplicity, as being 1. This is the graph that we saw earlier. And if we were to take a close look around the intercept at 3, what we would see is that the graph passes through that intercept, and not only passes through, but passes through in a sort of diagonal fashion. Now, the function is not linear here, but it's very close to it. And there is a slight curvature to it, but for all intents and purposes, when we're very near the intercept, the graph is almost a diagonal line. So if we have a multiplicity of 1, we're going to pass through the intercept in a diagonal fashion. This is example 2 from earlier. Let's take a look at the factor x minus 2, which has a squared above it, or as we say, a multiplicity of 2 for that particular root. You'll recall that the graph looked like this, and if we were to take a closer look at that intercept, we would see that it doesn't actually cross the axis, but rather it passes through the intercept horizontally without crossing. And that's true in general whenever we have a multiplicity of 2. You can expect your graph to pass through horizontally but not cross. Taking a look at example 3 from earlier, whose graph looked like this, notice that we have a multiplicity for the factor x minus 1, or I should say for the root of 1, we have a multiplicity of 3. If we take a closer look near that intercept, what we'll see when the multiplicity is 3 is that the graph does indeed cross, but not diagonally. Rather, it passes through and crosses the x-axis in a horizontal fashion. Now, it's unlikely that you'll ever see a multiplicity above 3, although it depends on your problems and your professor. But I'd like to share a few additional results with you, and before you try to read them all, don't worry, there's a pattern. It turns out, first let's focus on the blue or even multiplicities. Those are all the same. In fact, it turns out to be a general fact, not just 2, 4, 6, and 8, but any even multiplicity won't cross the x-axis, but rather intersect horizontally without crossing. Now, as far as 3, 5, 7, and 9 multiplicity, and we could generalize this result to any odd multiplicity 3 or higher, the graph will pass through the x-axis in a horizontal fashion. The multiplicity of 1 is the unique outlier in a sense, and the only multiplicity in which we see the graph crossing in a diagonal fashion. So again, I don't think you'll ever see a multiplicity higher than 3, but this does paint a general picture for all multiplicities of roots for how the graph will behave near the intercepts. Let's now turn our attention to the concept of end behavior. Loosely speaking, end behavior refers to where the graph is going on the far right and the far left end of the graph. Let's first take a look at example 1, which you see here in factored form, which we saw earlier. When we graphed this function earlier, we got this result. Let's analyze the graph a little bit further to get a broader understanding of how polynomials operate. And to do this, I'd like to go back to the standard form, or the unfactored form of this polynomial. It turns out that the farther you get away from 0, in other words, as you're on the far right or far left end of the graph, the behavior of the graph tends to be dominated by the first term. And so this graph is going to look a lot like y equals 2x cubed, far, far away from the origin. And to get a sense of how this first term influences the values of the polynomial, let's plug in a large number, say 100, just to get a sense of what this might look like. What this shows is that this first term of this polynomial has a value of, I think that's 2 million if you were to work that out. You can check me on that. But that first term has a value of 2 million, and because it is the lead term with the highest degree, it's going to have a bigger impact on the polynomial values for large values of x than any of the other terms that you see grayed out in that first line. And so one can imagine, based solely on the first term, which is the dominant term in terms of the end behavior, that the bigger x gets, the bigger y is going to get. This arrow here at the end of the graph shows us just that as x gets larger, y is going to get much, much larger. To be more formal about it, we use the phrase, as x approaches infinity, y approaches infinity. Loosely speaking, the bigger x gets, the bigger y gets. On the other hand, let's examine the far left end of the graph by plugging in a number such as, say, negative 100. The value of this polynomial at negative 100 is going to be roughly equal to the value of the first term at negative 100, because that term dominates the further you get away from the origin. And if you were to work this out, let's see what we've got. A negative number cubed is a negative number. Times 2, a very big negative number. I believe this works out to negative 2 million. And the point is that this calculation shows that as x gets bigger and bigger into the negatives, y would be getting bigger and bigger into the negatives as well. You can see that reality manifested in the graph by the downward arrow here. And we make the statement that as x approaches negative infinity, y approaches negative infinity. Roughly speaking, this tells us that the more negative x gets, the more negative y gets. Notice that I'm not teaching you how to graph the functions here. I've already done that. I'm just giving a rational explanation for why the functions are as steep on the ends as they are. And in order to help you understand polynomial behavior a bit more, let's look at another example here. This is the second problem we saw today. It's currently in its factored form, but let's change it back to its standard form to get a sense of the end behavior. We can learn a lot more about the end behavior of a function by its first term, but we can only know its lead term if it's not factored, if it's expanded out. In this case, the polynomial will be heavily influenced by the first term, or the x to the fourth term, when x is a large number, far away from the origin. For example, if x is 100, I believe this works out to 10 million. You can imagine how high up that point would be. Now, there's nothing special about the number 100, but this thought process that I'm taking you through should convince you that as x continues to get bigger, that y continues to get bigger as well. And just as in the previous problem, we would say as x approaches infinity, y approaches infinity. Let's take a look at the other end of the graph. Let's examine, for example, the number negative 100. If x were negative 100 in this polynomial, the y value would be approximately what it would be by just analyzing the first term, which is going to have the big influence as we get away from the origin. And if we were to plug negative 100 to the fourth power, wouldn't that be a positive? I believe it's positive 10 million. The number doesn't matter. What matters is that this calculation confirms that the graph is in fact going upward on the left. And to use the language of mathematics, we would say that as x approaches negative infinity, y approaches positive infinity. And of course, we don't write the positive in front of the infinity, but that's the assumption that we're making there. And this is just a formalization of what's kind of obvious from the graph anyways. The more and more negative x gets, the more and more positive y gets. Let's look at our third example that we did today. And again, instead of looking at the factored form of the graph, let's take a look at the expanded or standard form of the formula that we're graphing here. So standard form of a polynomial gives us a good indication of what the end behavior is going to be, based solely again on the first term of that. So for example, if we were to plug 100 in for x, this would work out to, I want to say negative 10 billion. I might be off by a zero there, but it's a very big negative number. And what that means is, or what that confirms, is that the graph is going downward here. And it shouldn't be surprising that we can state that in a similar way as before. As x approaches infinity, y approaches negative infinity. Now let's look at the left side of the graph. To analyze the end behavior there, we can work this out. It's worth noting that the two negative signs you see there don't cancel each other. It's very common for students to look at this expression and say, oh, I see two negatives near each other. That must turn into a positive. But of course, we have to follow the order of operations, so we have to do negative 100 to the 5th power first. That would be a negative number, which when multiplied by the negative 1, indicated by the minus outside the parentheses, would yield a positive answer. And that confirms that as x approaches negative infinity, y is approaching positive infinity. As I mentioned, the end behavior discussed here is not so much a graphing technique. It's just a way to confirm that your graph is correct and to have a better understanding of how polynomials behave as we get further and further away from the origin. So in summary, it turns out that the end behavior of a function can be categorized by whether it's an even or odd degree polynomial and whether or not the lead coefficient is positive or negative. If we have an odd degree polynomial whose lead coefficient is positive, it's going to be rising on the right and falling on the left. I could use the same language as before, x approaching plus or minus infinity and so on, but I won't complicate the conversation with that again. If the degree is even and the lead coefficient is positive, your graph will be rising on both sides. However, if your degree is odd with a negative lead coefficient, your graph will be falling on the right and rising on the left. And finally, in this situation, when the degree is even and the lead coefficient is negative, the graph will be falling in both directions. You don't really need this table to understand where your graph is going at the end. I suggest, rather than memorizing this table, that you simply plug in 100 or 1,000 or negative 100 or negative 1,000 into the lead term of the polynomial, as you saw me do before. And the information that you see here with the colored arrows will be exactly what you'll find. So I present this chart because it's common in education to do it, but I also like to say that it's not something that you need to memorize. It's something that you can deduce by simply plugging in a very large positive number or a very large negative number into the first term of the function. The last thing we want to look at to better understand how polynomials operate is how many x-intercepts can we expect in any given polynomial, and how many local extrema. A local extrema is a local maximum or minimum, sometimes called a turning point. And if you don't know what that is, you'll see it in our first example. We're going to start with a 7th degree polynomial. Just so you know where this graph came from, I picked a 7th degree polynomial. I typed the formula into graphing software. I am not, however, providing the formula here because, first of all, you'll probably never be asked to graph a 7th degree polynomial. And the specific problem I graphed isn't as relevant as the general lesson you're going to hear about determining the number of intercepts and local extremes. So there is some 7th degree formula that I typed into graphing software and this picture came out. Okay, well first, let's look here. This is an x-intercept, and let's count them. 2 x-intercepts, 3, 4, 5, 6, 7. This 7th degree polynomial has 7 x-intercepts. Hold that thought. How about the local extrema? Here there's a local minimum, local maximum. Local minimum, local maximum, all these are called extreme points or extrema. And if we count them in total, there are 6 of them. Now, one thing that mathematicians have always been interested in is how is the degree of the polynomial related to the number of x-intercepts or local extrema in the function? Well, in this particular example, we see a 7th degree polynomial having 7 x-intercepts. Are those always going to be the same? Will the degree always be the number of x-intercepts? Perhaps. And why do we have 6 local extrema in a 7th degree polynomial? Will it always be one less than the degree? Perhaps. More to be determined as we go. Next, I randomly plugged a 5th degree polynomial into graphing software, and I got this. Let's analyze the number of intercepts and the number of local max and min points. Here's an x-intercept. We've got 1, 2, 3, 4, 5 of them. So we've got 5 x-intercepts. More on that later. Let's take a look at the local extreme points. Local max, local min, local max, local min, for a total of 4 local extrema. And again, mathematicians are interested in relationships, such as, can I tell the number of intercepts or local extrema of a polynomial function when I know its degree? Well, it does appear again that we have a similar pattern. We have a 5th degree polynomial with 5 x-intercepts. So the number of x-intercepts here is the degree. Is that always the case? Perhaps. And we have 4 local extrema, which is 1 less than the degree. Is that always the case? We'll find out. But one thing we've noticed so far, it appears as though the number of intercepts is the degree of the polynomial, and the number of local extrema is 1 less than that. Generally speaking, that is true, but what you see on your screen right now is not the full story and doesn't always need to be true. So to answer my earlier rhetorical questions, is that always the case? Not necessarily. Now we're going to look at 2 examples that seem to violate, well, they don't seem to violate, they do violate this general trend. Here's a 9th degree polynomial. I just randomly plugged some 9th degree polynomial in the graphing software, and this is the picture it gave me. Let's go ahead and count the relevant items here, starting with the intercepts. X-intercepts, 1, 2, 3, 4, 5, 6. So this 9th degree polynomial only has 6 x-intercepts. Now let's analyze the local extrema. Local minimum, local maximum, local minimum, max, min, max, for a total of 6. So what this problem shows is if we compare the degree of the polynomial to the number of intercepts and local extrema, that it doesn't necessarily have to be that the number of x-intercepts is the same as the degree and that the number of extrema is 1 less than that. More on that later as we look at one more example. Here's a 4th degree polynomial. Some random thing I decided to graph. Notice it has 2 x-intercepts and 3 local extrema. Again, what is the relationship between the degree of the polynomial, the number of x-intercepts, and the local extrema? Well, I think if I've showed you anything in the last 4 examples, is that there's a lot of variation to this, and that there's nothing that we can 100% count on just by knowing the degree of a polynomial. However, mathematicians have proved that there is one thing that we can count on, when it comes to these two questions. Let's consider what we call an nth degree polynomial, which really just means let the number n represent the degree of the polynomial. It turns out mathematicians have proven, which I will not prove here, but mathematicians have proven that if you have an n degree polynomial, then the number of x-intercepts is at most n. You can't have any more than that. In other words, an 8th degree polynomial could have 8 x-intercepts, but it could have less than that, anything from 0 to 7. And further, for an nth degree polynomial, the number of local extrema is at most n minus 1, meaning 1 less than the degree. So if we have a 5th degree polynomial, we could have no more than 4 local extrema. We might have less than that, but that would be the most that we could have. And I hope this summarizes the relationship, as best one can, between the degree, the number of intercepts, and the local extrema. In this video, I've strived to give you as much information as I can for you to understand the nature of polynomials and how they behave. Before I end the video, I'll simply say that when it comes to just graphing, if all you want is the sketch of a graph of a polynomial, you could pretty much just do what we did in the beginning of the video. Find the intercepts, plug in numbers between the intercepts, decide if the graph is above or below the axis, and graph accordingly. The latter half of this video was designed just to give you a sense of polynomial behavior and some of the reasons why the graphs are the way they are. And I hope it's been helpful. Thank you so much for watching.